Okay, today we're looking at section 9.1, properties of radicals, day 1. Okay, to start out, a radical expression is an expression that contains our radical, and the radicand is the numbers or numbers in variable or variables that are underneath the radical. A radical is going to be considered in simplest form when the radicand has no perfect squares underneath. So if we look at the example square root of 80, 80 can be factored as 16 times 5. Now the square root of 16, this is a perfect square, so we can rewrite square root of 16 as 4 times the square root of 5. No radicands can contain fractions, so under the radical, we don't want to see any fractions. In addition, we don't want to see any radicals in the denominator. Let's look at the product property of square roots, which says that the square root of a product is equal to the product of the square roots of the factors. So if we look at numbers, if we have the square root of 9 times 5, this is equivalent to the square root of 9 times the square root of 5. Breaking it up into two pieces, square root of 9, 9 is a perfect square, so this simplifies to 3 times the square root of 5. Algebraically, we can see if we have the square root of a times the square root of b, this is equivalent to the square root of a times the square root of b. Okay, let's go to example 1. We have the square root of 147. We can rewrite 147 as product of its factors. So 147 factors to 49 times 3. We can use our product property of square roots, and we have the square root of 49 times the square root of 3. Square root of 49, well 49 is a perfect square, so this is 7 times the square root of 3. Next one we have square root of 9x cubed. So this is equal to the square root of 9 times x cubed. We can use the product property of radicals to rewrite this as the square root of 9 times the square root of x cubed. Since 9 is a perfect square, the square root of 9 is equal to 3. X cubed can be written as x times x times x. Since there's a matching pair, we get to take 1 out of the radical, and we're left with 1 underneath the radical. So simplifies to 3x times the square root of x. Okay, next we're going to look at the quotient property of square roots, which says the square roots of the quotient equals the quotient of the square roots of the numerator and denominator. So we have the square root of 3/4. We can break this up into the square root of the numerator, square root of 3, over the square root of the denominator. And if we look here, square root of 3, we're going to leave it as the square root of 3, but the square root of 4 is equivalent to 2. So in simplest form, the square root of 3 over 2. Algebraically, we see that if we have the square root of a over b, this is equivalent to the square root of a over the square root of b. When a is a positive number, so it's greater than or equal to 0, and b has to be greater than 0. Using the quotient property of square roots, we have the square root of 11 over 36. We can rewrite this as the square root of 11 divided by the square root of 36. The square root of 11 is in simplest form, so we're going to leave that, but the square root of 36 is equivalent to 6. So we end up with the square root of 11 over 6. The next one, we have the square root of 144 divided by n squared. So this is the square root of 144 over the square root of n squared. 144 is a perfect square, which is 12. Square root of n squared is n. Okay, now we're going to look at some cube roots. So we have the cube root of 135. So we can simplify this as the cubed root of 27 times 5, which is equivalent to the cubed root of 27 times the cubed root of 5. Cubed root of 27. Well, 27 is 3 times 3 times 3. Since there's 3 of these, it can come out of the cubed root. So we end up with 3 times the cubed root of 5. Next, we have the cubed root of 8x to the 4th. So we're going to rewrite this as the cubed root of 8 times x to the fourth, which is equivalent to the cubed root of 8 times the cubed root of x to the fourth. So cubed root of 8. 8 is a perfect cube. It's 2 times 2 times 2, so we can simplify this as 2. Cubed root of x to the fourth. X to the fourth has 4 x's, so we can take 3 of these out, so we end up with 2x, and then we have the cubed root of this remaining x underneath the radical. Next, we're going to look at the cubed root of n squared divided by negative 1,000 using the quotient property for radicals. So we're going to rewrite this. Cubed root of n squared divided by the cubed root of negative 1,000. So the cubed root of negative 1,000, this is actually negative 10 times negative 10 times negative 10. So this is a perfect cube. So we're going to leave the numerator, cubed root of n squared. We can't take anything out of the radical, but we have negative 10 in the denominator. Okay, so our last problem, we have the cubed root of 343 a to the 8th divided by b cubed. So we're going to rewrite this as the cubed root of 343 a to the 8th power over the cubed root of b cubed. Okay, next we're going to use the product property of radicals in the numerator. So we have the cubed root of 343 times the cubed root of a to the 8th power. All of this is still over the cubed root of b cubed. Okay, so the cubed root of 343 is a perfect cube. It's 7 cubed. 7 times 7 times 7, so we end up with 7. Cubed root of a to the 8th. So a to the 8th, this is 8 a's. So it's a times a times a times a, and then 4 more. All right, so if we think about this, these 3 a's, we're going to be able to take an a out of the radical, and then we have 3 more. We're going to take an a out of the radical. So we're left with 2 a's underneath the radical. So we have a times a outside of the radical, which is a squared, and we're going to have cubed root of a squared underneath. And all of this is going to be over the cubed root of b cubed. B cubed is a perfect cube, so it's coming out of the radical, so we end up with a b. So our answer is 7a squared, the cubed root of a squared, over b.